Today on This Week in Space, we visit Nancy Chabot of the Johns Hopkins Applied Physics Laboratory to talk about NASA's amazing DART mission.
Podcasts you love.
From people you trust.
This is TWiT.
This is This Week in Space, episode number 33, recorded on October 14th, 2022, DART's Bullseye. This episode of This Week in Space is brought to you by Melissa. Poor data quality can cost organizations like yours an average of $15 million each year. Make sure your customer contact data is up to date. Get started today with 1,000 records clean for free at melissa.com/twit. Hello and welcome to another episode of This Week in Space, this one called DART's Bullseye. I'm Rod Pyle, editor-in-chief of Ad Magazine, and I'm joined as always by the insuperable Tariq, Malik, editor-in-chief at space.com. Good day, Tariq.
Hello. Hello. Nice to see you, Rod.
Good to see you. And today we have the honor of being joined by Nancy Chabot. She's the planetary chief scientist and coordination lead for the DART mission at the Johns Hopkins Applied Physics Laboratory. Thanks for joining us, Nancy.
Oh, thanks. It's really good to be here.
It's great having you, and I really appreciate you taking time out of what has to be a very busy asteroid smashing season for you, so we really appreciate it. But before we begin our impactful discussion, sorry about that, I have a space joke. This one was sent by loyal listener Ken Kramer in Los Angeles. How you doing, Ken? And here we go. Hey, I spotted a new article about an asteroid colliding with Earth. I couldn't read it, though. It hits too close to home.
Oh, that's good.
Yay!
I love it.
You got the drums. The drums.
You're very polite, Nancy. Usually I get crickets, so I appreciate the drum roll, Aunt. All right. And a reminder, some of you have written in saying you enjoy the space jokes, others not so much, which I completely understand. So here's your chance to show us how it's done. Give us your best shot and send us your joke of choice to TWIS@twit.tv. That's TWIS@twit.tv. And each week we'll pick one or two of the best jokes and read them on air with credit to you. All right, let's get through a couple of headlines. Hey, Tariq,
Yes.
how about an Artemis update?
Well, in the Artemis Space Star Trek chair update, I fixed the chair, Rod. So there's at least that. But we do, in fact, have a new Artemis 1 moon rocket launch date. NASA announced this week that November 14th. So now we are firmly into next month as we're recording this now. November 14th is the launch date. This came from space.com, but also from NASA because they're the ones that announced it. The window actually goes through like Thanksgiving, the 27th or so, for Artemis. But if they do launch on the 14th, that's like a 12:07 a.m. launch. That's like a midnight launch. And they only have about an hour and a half, about 69 minutes to launch this mission. So kind of weird they would target this because NASA has told us several times that this is the first launch of Artemis 1. They wanted to do it in the day to watch and see how the whole system works, but I guess they'll settle for the nighttime if that's the earliest that they're going to be able to launch it. So they picked the 14th, the 16th, and the 19th of November as the initial launch days. And if you're wondering about those two gaps, that's because it takes 2 days to refuel the tanks for the liquid hydrogen, massive amounts that they need in the storage tanks. You know, if they fuel for a launch, then they have to kind of gas up. It takes a couple days for that.
Very good. Well, fingers crossed, and we'll have to make a new bet for that chair now that you actually bothered to fix it. Next up, a Mission Impossible in space. This one from space.com. And the ultimate high-wire do-it-yourself stunt. Top action star Tom Cruise is a step closer to performing his ultimate stunt, a spacewalk. The filmed entertainment chief at Universal Studios has made it official. Yes, the studio wants to send Tom the Terror into space to perform a spacewalking stunt outside the International Space Station, in which he will, as the plot goes, be saving planet Earth. How original. Go big or go home. The film is still in development, which is an indistinct term if you know anything about Hollywood, but it's moving along. Assuming it happens, Cruise would be the first civilian to step outside a spacecraft in Earth orbit, unless the Jared Isaacman's mission beats him, but hopefully this will happen first. Tom has a long-standing interest in space, having narrated at least one IMAX documentary about the International Space Station and, of course, serving as a governor for my homies over at the National Space Society for many years. SpaceX appears to be game for the mission, and I can only imagine the stunt insurance bond for this one, which is something that he's famous for because he's an expensive guy to replace if something goes wrong. So we'll stay tuned on this one.
Yeah, and the timing is really weird because they say that he's going to be the first civilian to do a spacewalk, but we know that Jared Isaacman said that that SpaceX, that private SpaceX Dragon mission, will do a spacewalk in orbit, and they've already named the full crew for that. That mission right now that they announced is looking like it's the first quarter of 2023, which would not leave a lot of room between now and then for Tom Cruise to fly into space and then to do a spacewalk out of the International Space Station. So either that Isaacman flight's gonna drift a bit later, or they've got something in that they're hiding in the wings about what flight he's actually going to be on and who's going to go, or when that's going to go.
Well, maybe he can go down in the books as the first guy to do a private spacewalk from the ISS. We'll go for that.
Yes. Well, there you go.
Our last story comes from Ars Technica, one of our favorite online journals. In more Citizens in Space news, early space tourist Dennis Tito and his wife Akiko have signed on to fly aboard SpaceX's second circumlunar flight. His other space flight was aboard the Russian Soyuz 20 years ago, and he spent a week aboard the ISS. When asked about would he go back to the ISS, Tito said he would not care to repeat that experience. Didn't say why. Nor would he have an interest in landing on the moon, he said, if that was on the table, which is not. But the single looping flyby was just his cup of tea. His wife Akiko, who's a qualified pilot herself, was just as excited, and I sit and look at this in great envy.
This is interesting because the Dennis Tito and Akiko both had like a press call after this news came out on earlier this week, and it wasn't like that Tito didn't like his trip to the space station. It was that he's been there and done that and didn't want to go to orbit again. He wanted like a new experience. And it sounds like this trip kind of came out of nowhere. The two of them were touring SpaceX's Starbase, where they have all these big starships under construction. And it just kind of came up in conversation, like, would you like to go to space again? And Akiko was like, it'd be nice to go to the moon. And it's like, all right. So it's kind of nice if you got billions of dollars to spend. He did not say how much he's paying and said that he's not going to say how much he's paying. They did not say if they're launching out of Florida, where SpaceX is building a new Starship launch site, or out of Boca Chica, Texas, where they have one already and they're doing their testing. So there's a lot of things that still need to be answered for this flight. And we should mention they still haven't launched a Starship yet, SpaceX. So they're looking to hopefully get that done into orbit later this year.
Not much of this year left.
That's right. They did say that they were targeting maybe November for an orbital flight, but they still haven't tested the full Super Heavy booster with all 33 engines yet, and that's a big step in order to show that your rocket is ready. They did stack this week, we should mention, Starship on top of Super Heavy again, the one that are going to fly, and so that's at least a step forward, but that could just be some mating tests for it, or maybe even just some vibration tests to see how the stack is doing.
Very good. Well, that wraps up our headlines, and we will be back to speak to the very patient Nancy Chabot after this short message, so stay with us. This episode of This Week in Space is brought to you by Melissa. Melissa is a leading provider of global data quality and address management solutions. Did you know that poor quality data can cost organizations an average of $15 million each year? If you're a small to medium-sized business, we know you need every last cent. The longer poor quality data stays in your system, the more losses you can accumulate. Melissa will never cost you more than you're going to save. To ensure your business is successful, your customer information needs to be accurate, as high-quality data will save you money. And there's another side to inaccurate data, and that's customer service. If you address someone with the wrong name or verify the wrong address when dealing with an already frustrated customer, things can go from bad to worse in a hurry. Check out Melissa's cloud-based data cleansing and enrichment tool. It's really easy to use. Step 1, upload your file in either Excel or CSV into the first tab, or copy and paste your data as CSV into the second tab. Step 2, select Data Quality Service and click Next. Step 3, map the input fields. Step 4, select output fields and data to append. And Step 5, process your list. Melissa's Data Quality Suite will help eliminate clutter and duplicates, reducing postage and mailing costs. You'll also get batch address cleansing, which will process an entire address list for accuracy and completeness. name verification, which will parse and standardize first and last names for personalization, profiling, which will analyze your data to improve its quality over time, and email verification, which will remove up to 95% of bad email addresses from your database. Melissa's flexible deployment options offer different platforms to suit any preference, business size, or budget. Melissa also has their new Lookups app on iOS and Google to search addresses, verify social security numbers, access detailed property data, and more right at your fingertips. Melissa continuously undergoes independent security audits to reinforce its commitment to data security, privacy, and compliance requirements. They are SOC 2, HIPAA, and GDPR compliant. Melissa's data quality suite and clean suite speaks for itself, but it was once again named a leader by G2. Melissa is experienced, independent, and has 37 years of data quality expertise, which explains why more than 10,000 businesses know them as the address experts. And if you sign up for a service level agreement, you'll get 24/7 world-renowned support from their global support center. Make sure your customer contact data is up to date. Get started today with 1,000 records clean for free at melissa.com/twit. That's melissa.com/twit. And we're back. Thanks for staying with us. Tariq, take it away.
Yeah. So very excited to have Nancy here with us to talk all about the DART asteroid impact mission. I think if dear listeners, you've been following us, you know that we talked about this mission a little bit earlier when the NASA's DART asteroid spacecraft did crash into the asteroid moonlet Dimorphos. Big success. And this week, by sheer coincidence, because we had been trying to get Nancy on to talk about it for a while, by sheer coincidence, we got a great big update that said that it was a resounding success, that humanity has for the first time moved an asteroid by smacking into it to show that we can do that. And Nancy, you were here to dish all the amazing stuff on it. So thank you so much for joining us. And I think, the best way to start out, I was wondering, is if you can kind of give our listeners a reminder of what DART, the double asteroid redirect test, really was, and why you and the Johns Hopkins Applied Physics Lab team, actually did this to go smack an asteroid out there 11 million miles from Earth.
Yeah, so DART is all about planetary defense. So this is if you found an asteroid that was heading to the Earth in the future, you would potentially want to prevent that from happening. But how might you do this? And so DART is demonstrating one technology, and I should say has demonstrated. I have to get used to talking about this in the correct verb tense. DART has demonstrated one way to potentially deflect an asteroid from hitting the Earth in the future if this was needed. And so this method is called a kinetic impactor technology, which is just a fancy way of saying crashing a spacecraft into an asteroid and giving it a small nudge. And that's exactly what DART did. And it's really exciting that we've taken this first step to demonstrate moving an asteroid ever so slightly in space.
And to give people a picture, how fast did you hit this asteroid for? Why this one asteroid, and how big was DART in the first case to be able to move an actual ginormous asteroid?
So the DART spacecraft is about the size of a small golf court. It's actually a very human-sized spacecraft. Is actually how I think about it a lot. At the Johns Hopkins Applied Physics Lab, it was built. One of my favorite photos that I use a lot when I talk about DART is, looking up at the spacecraft, and it's sort of the size of a person, about 6 foot by 6 foot by 6 foot. Sort of on all of the sides. It's got some really long solar arrays, but they don't have a lot of mass in them, so they don't really contribute. And then it crashed at 14,000 miles per hour into something about the size of the Great Pyramid or a sports stadium, or, it's a little bit less than 2 football fields in length, but much bigger than this very human-sized spacecraft. And so you might think, well, okay, how does this little golf cart-sized spacecraft move something the size of the Great Pyramid? And the answer is it doesn't move it very much. It's really this is all about asteroid deflection, not disruption. You're not trying to blow this thing up. You're not trying to do a lot to it. You're trying to just sort of, shove it slightly so you don't make your problem any worse than you need to be, but you just change the motion ever so slightly. And this is the sort of thing that if you did want to do it, you'd do it years in advance or decades in advance, such that you don't do very much to the asteroid except change it ever so slightly. And then that would add up to a bigger change in its position with time. And then the collision course with the Earth and the asteroid would be avoided. So This is what DART was demonstrating. This is what DART successfully demonstrated, which I'm sure we'll get to how successful it was and how much we moved that asteroid. This double asteroid system that it went to was a great way to do this first test because the two asteroids there let us deflect a small asteroid around a much larger one. And that's a much easier measurement to make from the Earth. So we were able to really get a quick measurement on how much we deflected that asteroid. If you were doing this in the future, potentially if you needed to, you would deflect how that asteroid went around the sun. So it's a similar sort of thing. It's just much easier to make that measurement, and also a really safe way to do this first test. Because even though we have changed how an asteroid moves in space, we've just changed how it goes around a much larger asteroid. It's now even more gravitationally bound to that larger asteroid than it used to be.
Well, you mentioned your success. So yeah, I don't want to keep everybody a mystery. So I'm sure you modeled this to death before you sent the spacecraft.
We are scientists, so yes, absolutely.
Yeah,
we did that.
But your results were better than expected, which is, of course, after a certain point, this is what people come to expect from NASA and from your laboratory. It's like, oh, your results are better than expected. That's what we expected. But can you tell us about what actually happened now that you've had a chance to observe and refine your data?
Yeah, so I think it's a really spectacular result, and we're all very excited about it. If it's better than expected, I think people on the team would quibble with that a little bit because the papers that are published and out there before DART even impacted the asteroid had a really huge range of predictions that were published, and so this value is within that range of published predictions. That said, if it's very clear that we're getting more deflection than just what this little golf cart sized spacecraft brought in itself. And I think that's what people are so excited about, is that if you just brought in this spacecraft and just that mass and just that velocity, you wouldn't be getting this 32-minute period change that we're seeing. You would get something more on the order of 7-8 minutes or something like that. So this is considerably more deflection that you're getting, and it's getting enhanced because of all of the ejecta that also came off with the DART spacecraft. So the DART spacecraft went in there, but it threw a lot of rock and dust and material off, and that kind of serves as a little jet that also helped with the deflection and really enhanced the amount of deflection and push that you're getting. And so in that sense, I think how much that is contributing is really the exciting result that people are celebrating.
So you gave Dimorphos its own propulsion system, in effect.
Yeah, a little bit. A little bit of using
cool.
a bit of Dimorphos to help nudge it a bit.
I just wanted to clarify. You said 32 minutes there in terms of like the change, and what I had read previously is that the hope was that you would accelerate Dimorphos in its orbit. It's an 11.5-hour orbit. Am I correct? Around Dimorphos, you would accelerate it so it would be about like 73 seconds faster. But you said that you're 32 minutes faster. That sounds like a lot more than what your baseline hope was for the mission itself. So,
yeah, there's a lot to unpack there. So let's see. Before DART's impact, it was 11 hours and 55 minutes that Dimorphos would go around Dimoprhos. So it was 11 hours and 55 minutes, and it had been like that for as long as we had been observing this asteroid since 1996. So it was just happily out there in the solar system doing its 11-hour and 55-minute thing. The DART spacecraft came in, and what we reported earlier this week, we've measured that Dimorphos now goes around Dimoprhos every 11 hours and 23 minutes. So this is a period change of 32 minutes that we've caused in order to do this. The requirement for the mission was 73 seconds. And the reason the 73 seconds came from was because that was sort of the minimum that you would be able to measure using the telescopes here on the Earth reliably. So that requirement was set by making sure that you deflected enough so that you could make a measurement successfully. How much you deflected it is really why we wanted to do DART. So we didn't really go in with the expectation of, how much is this? It's because that was the fundamental answer that we needed to get. If it was going to be less effective than we thought or more effective than we thought, as long as we could measure it, then the mission would have been a success, because that's the important information. And that's where the 73 seconds comes from. Most people did not think that just from bringing the spacecraft in itself, if you were able to hit it squarely, right, which we should take a step back and just acknowledge the challenge that goes into hitting a small asteroid in space that you've never seen before, and you can only see during the last hour of the mission through autonomous navigation squarely head on, right, which is a challenge in itself. But if you did that, then just from the spacecraft mass and its velocity, the momentum would have resulted in about a 7 or 8 minute period change, people think. So there's a lot of numbers there that I just kind of threw at everybody. But the take home is that the 32-minute orbital period change definitely means that the amount of ejecta coming off is enhancing the deflection. And that's a really promising result for planetary defense and potentially using this in the future.
You mentioned the feat of just the act of smacking an asteroid 11 million. I mean, you launched the mission in, a year ago in November of 2021, and you hit it. I think it was like 7 meters, right off the ground zero. And I'm wondering what that felt like for you and for the team, because I was in that press room and people were like chanting in the last few seconds, like go, go, as if it wasn't going to happen because you were already on target. But
it was still pretty small until the very end, right? I mean, even within that last minute when you were watching it, it still was very small. It wasn't filling up the whole field of view, right? I think that's part of it, is that you were coming so fast and an object so small. And you could see it was on course, but you could also see lots of empty space around in that image still, right? Leaving open this possibility. And this was a huge technological challenge and a really important part of DART, where, this week we've been talking a lot about how much it deflected it, but just that act of targeting a small asteroid that you've never seen before in space at high speed and successfully targeting onto it autonomously is a huge accomplishment, and also very promising for using this technique going forward, and made for an incredible moment that, I think I didn't fully appreciate just how special it was that NASA was able to share that moment live with people everywhere around the world. And a lot of people had this individual experience in this individual moment. All age ranges, right? We've heard from kids, we've heard from, grandparents, we've heard from everybody around the world. And, I think that's experience that we've shared with humanity and that people will remember.
Yeah, definitely. Definitely, for sure.
So the magazine I write for at Astra, we write about planetary defense a fair amount, at least a couple times a year. And it's, the challenge is always to try and convey why it's important, which you wouldn't think would be that difficult, right? You show a picture of a big crater. The typical thing is to show a picture of a crater in Manhattan. This is what would happen if something this size hit the planet. But it can still be a challenge to get people excited about it. Can you talk a little bit about what planetary defense is and why it's so important?
Yeah, planetary defense is just dealing with the natural hazard that exists from asteroids and comets that hit the planet. This is not new. This has been going on for billions of years, that Earth has been hit by these objects, and it will go on in the future. And so it's sort of a question of what can we do to potentially prevent or mitigate against this natural hazard that exists. And so planetary defense is not just all about crashing spacecrafts into asteroids. It's about identifying the asteroids, assessing them, characterizing what they're like. Working internationally is a huge important part of planetary defense as well, because this is a planet-wide issue. And then there's mitigation, doing something about it if you identify one that you need to. It's important to say that of the asteroids that are currently being tracked, none are a threat to the Earth for the foreseeable future. But of objects about the size of Dimorphos that DART just successfully demonstrated asteroid deflection on, we've found actually less than 40% of that population of asteroids that size. And so along with taking these steps to potentially be able to prevent those asteroids from happening, you need to know where those asteroids are to be able to do something about them and know they're a threat in the first place. So there's still actually a lot of important work, fundamental work that needs to happen for planetary defense in identifying these asteroids and tracking them, so we have that information to potentially be able to do something about them.
Well, and I guess that brings us to the topic of Surveyor, which has been something that's been proposed for a long, long time under a variety of names. And my understanding is that it's moving forward, but it's not yet fully funded. Do you have any thoughts on that?
I think, I can say that from studies that have been done for over decades now at the National Academies of Sciences and every other study that's been done, there is complete agreement that the number one priority for planetary defense is to find the asteroids. And the most effective way to do this is with a dedicated space-based infrared telescope. And so this has been an important thing to do for a long time. And it's great that NASA is supporting a NEO Surveyor. And the sooner that can happen, in my personal opinion, the better.
Yeah, I mean, just look at how many asteroids the WISE spacecraft found when it was in its extended mission, when they had NEO-WISE, and that was just prolific, and that was the end of that mission. So a new one, you can imagine, would be able to find a lot more. So.
Yeah, and it's really kind of a unique capability. Sometimes maybe people think, well, we have space telescopes. Why can't we just use those, right? And it's like, no, those space telescopes are designed to look at things that are really far away, right? Like look to the beginning of the universe and all of that, right? Galaxies and these sorts of stuff. That's a very different technique and technology than you would use to look for the objects that are coming closest to our planet. Which is why really a dedicated space-based asset that just does that and does it really well would be very effective to really identify everything 140 meters and larger. This is a goal that's completely achievable. And once we do that and you identify them, you have good knowledge about them. It's completely realistic to understand where these objects would be for a timescale of 100 years. And now all of a sudden you are in a position to have planetary defense be where you have this warning time, and then you can go use something potentially like the DART technology of the kinetic impactor, where you give a small nudge many decades in advance and can prevent the Earth from being hit by asteroids.
Yeah, I wanted to follow up on that, Nancy, because you mentioned kind of how this was the first of its kind test of this kinetic impactor, and I'm wondering how the DART mission, like what the origin story is at Johns Hopkins University Applied Physics Lab, to kind of conceive of the mission, where instead of going to smack an asteroid going around the sun, which is what I would think of about, in terms of like a demonstration, you target this I guess it's a binary asteroid. Is that what you would call Didymos and Dimorphos? And I'm wondering, like, when did that first seed, get planted, and then how did it become the DART mission that we saw slam into the asteroid this past month?
Yeah, the whole idea has actually a really rich and international history. There were missions that came before DART and concepts for missions that came before DART that involved a lot of international collaboration because people, like I said, asteroids hitting the Earth is not a new thing. People have known about this for a while. People have wanted to develop the technologies to potentially prevent this for a while. And a lot of the early concepts did look at, potentially deflecting how an asteroid would go around the sun. The issue is then you need potentially a second spacecraft around in order to figure out and measure that deflection. So then this becomes a more costly endeavor, a more complex endeavor that requires two different spacecraft in order to be accomplished. And so people really wanted to do this and were stressing the importance of it. But then that also made it a much higher and more costly bar in order to get over. So there's this great story actually about my colleague at the Johns Hopkins Applied Physics Lab, Andy Ching, who came up with the idea of using a binary asteroid system to do this instead, while exercising in his basement. So he was exercising in his basement, and then the idea just came to him. Since then, he's been asked many times about, like, what sort of exercises were you doing? Why were you thinking this way? And I don't know. I think maybe it was just a good time for him to think or something like that. But it was kind of like this ingenious idea all of a sudden to be like, oh, hey, let's do this in a way that's easier to measure. And we'll use telescopes that already exist here on the Earth that are all really good at looking at these sorts of asteroids in order to make that measurement. And now all of a sudden you've allowed yourself to just have one spacecraft and have a highly focused mission where that spacecraft is good at doing one thing, which is finding that asteroid and crashing into it. But you're using all of these other assets that already exist, without having to build them up from scratch. So this is a much more cost-effective solution to enable this first step to be taken. And so this idea, Andy actually went to an international conference about planetary defense and shared it with a bunch of international scientists there, and everybody got very excited. And there was actually going to be a European Space Agency mission that would go the same time as DART and already be there. It was named AIM. And so it would still watch because we want to get a lot of information. It wouldn't necessarily make the deflection measurement because you could use telescopes on the Earth. And so there was going to be DART and AIM, and they would go together. Unfortunately, AIM didn't get the funding that it needed over from the European Space Agency, but NASA was able to move forward with DART. And then, happily, the European Space Agency has been able to fund Hera. So Hera is a European Space Agency mission that's going to arrive in the Dimoprhos system in 2026, and it'll stay there. So that's what's so exciting too, is rather than just being a crashing mission or LiCube that just sort of flew by and took some spectacular images, Hera will stay in this system and be able to get the mass of Dimorphos, be able to see the crater left by DART, be able to really characterize the system and follow up on the DART test. And so we'll learn so much more from that international collaboration. So I think everything has an interesting origin story, and I think one of the lessons learned here too is not everything is straight, right? It's always this curvy path of an idea and it didn't work out, and an idea it didn't work out, and sometimes there's really some pretty extreme disappointments along the way when you are invested in a project and then maybe it doesn't get the funding that it needs in order to succeed. But at the same time, it's also a story of everything building off of each other, each of those steps, each of those conversations, each of them leading to then, some project like DART, which actually then has demonstrated this now and has been successful.
Well, I've got some questions about the spacecraft itself, but first we're going to take a short break, so stay with us. So if you follow the work of places like JPL and its associates, like your laboratory, we're used to seeing spacecraft that are jammed with instrumentation. They're constantly doing these trade studies about, okay, if we save an ounce here, we can put a little bit more on this instrument and an additional lens with the other 30 lenses inside this telescopic camera and so forth. DART was a little simpler, but it wasn't a cannonball. I mean, it's still a spacecraft. So you could talk a little bit about what was on DART, the instrumentation, and the Italian CubeSat that flew along with it.
Yeah, so the DART spacecraft was a pretty highly focused mission to meet these planetary defense objectives. But it had a few other distinct items on it as well. It was the first flight test on a deep space mission of the rollout solar arrays, which were these solar arrays that are kind of like a aluminum foil tube that you have in your kitchen. When they were launched, they were all rolled up, and then they extended out, and they were 28 feet tip from tip once that happened. And so that was a cool new technology that was on the spacecraft. There was also the first flight of NASA's Next-C ion propulsion engine. And so we were able to demonstrate that and get some first hours on it. But both of these were sort of secondary to the main payload on DART, which was Draco, the Dimoprhos reconnaissance and asteroid camera for optical navigation. This is a camera that was built at the Johns Hopkins Applied Physics Lab, learning and sort of similar to the one that was on the New Horizons missions that took the spectacular images of Pluto. So using that great telescopic design, that's the camera that was needed. And this wasn't just a nice to have to see what the asteroids looked like, but was a necessity for the autonomous navigation system called SmartNav, the small body maneuvering autonomous real-time navigation, the brains of the spacecraft. The images from Draco were fed into that SmartNav system, and then SmartNav had to identify the asteroid and autonomously fire the thrusters in order to ensure that it intercepted Dimorphos and not Didymos. And it was only within that last hour, like we saw, that it could separate Didymos from Dimorphos rather than just seeing a single point of light in those Draco images. Those are the same images that were streamed back that we all watched in spectacular fashion. But at that point, the spacecraft was driving itself. It was flying itself. It was firing its thrusters autonomously. It was maneuvering in order to ensure that it was on that intercept course with Dimoprhos. And that was the most important parts of the DART spacecraft as far as a payload goes. It's having that really great camera with that great telescopic capability, so you could pick out Dimoprhos as soon as you possibly could in order to get those thrusters as much times as possible with that autonomous navigation to work. So then also on DART was LiCube, the Light Italian CubeSat for imaging of asteroids. And it's contributed by the Italian Space Agency. It's a briefcase size mini spacecraft. It has 2 cameras on it, and it was released 15 days before DART's impact. And this was enough time for it to get away from DART and get itself calibrated. And it witnessed and took images of DART's collision and then made its close flyby about 3 minutes later at about 50 kilometers away and captured these spectacular images that we've seen now of the ejecta and how it was streaming off from the surface of Dimorphos and getting the structure. And there's still so much work going on to try to understand that and understand what it means for this actual impact event and what that means for applying it to others in the future. A lot of LichioCube images have been sent down to Earth now, but LichioCube stored all that data on board. And then once it did its close flyby, it's been sending them back to Earth over the last weeks and days. And that'll continue for another few weeks before we actually even have the full data set down.
Oh, what happens to LichioCube now? Now that it's going off on its own?
Well, now it's sending its data down first. And then, after that, I think the Italian Space Agency will assess what makes sense for there. I don't have insight into their fuel levels or what might be possible, but they were definitely focused on doing everything they could to capture DART's impact event. So I just don't know what their capabilities will be once they get all of the data back found for DART.
So it sounds, just from what you've described, that not only was the DART mission kind of a scientific success to test this idea of crashing into an asteroid, but it was, by all accounts, it seems an engineering, like hole in one. You've got this camera that has to be able to pick out an asteroid that you've never seen before, only like a little bump, right, on another bright blotch in a telescope image from the past, and then this ion drive and these thrusters that have to switch on autonomously to power that last hour into the asteroid, and then this navigation system to make all that work. I mean, it sounds like you checked all your boxes. If I'm hearing you right for this, and now there's a toolkit to use if we find another pyramid-sized asteroid that's coming our way.
Yeah, exactly. This autonomous navigation, small asteroids that you have limited prior information about that you would need to target is completely relevant for planetary defense. And it's that technology development was a huge advancement that the Johns Hopkins Applied Physics Lab team made in order to do that, especially with the smart nav capability. And a lot of testing. I mean, you might imagine they didn't know what Dimorphos looked like. As you said, it was never really resolved in the optical telescopes. In radar, it was always just sort of, 2 pixels. And so they had to do so much testing, that team at APL, different shapes of Dimorphos, different lighting conditions, just trying to do everything. And it performed fabulously. I think that is probably the biggest challenge that the mission had. I think we thought and we're pretty confident that if you hit the asteroid that you would move it slightly. How much is the important information that we've been trying to figure out? But that's a different question than just that straight up technology challenge of hitting something in space that you have such limited information about. But that also might be the situation that you'd be in for planetary defense. In fact, even for planetary defense, it might be that you're not actually trying to hit it. But if you did find an asteroid, one was identified, and it was on a potential threatening path for the Earth in the future, and if you had the time, one of the things you might do is just want to launch a spacecraft really quickly, rapidly, and do a quick flyby and see what this thing looks like, because you'd be in so much better shape if you just got even the most basic information about that. But maybe you don't know its position very well, so you're not sure. And this autonomous navigation is exactly the same sort of thing that you could use just to do a close flyby of an object rather than intercepting it, and enable a rapid response mission like that to characterize what you're dealing with.
So to build on that then, because now you've got like an after action report with DART at Dimorphos. And I recall, like in those last few days, you and other scientists on the team had said, several times, we don't know really what Dimorphos is made out of. Is it like a sponge, or is it a rubble pile, or is it a solid brick of a rock out there? What did DART show you of what the asteroid, and I would assume its parent, are made out of, because they would be maybe made out of the same stuff way back when at their formation. Is it a rubble pile? Is it a brick out there in space? Or do you still need to study the images from LichioCube to know more?
Well, people are studying both the Draco and the Lichia Cube images and doing all sorts of modeling. But on the team, from seeing those Draco images and just seeing how the surface looks like a big giant pile of rocks on Dimorphos, people think it's largely a rubble pile. How solid on the inside, how much of a rubble pile, how much macro porosity, how much pore space, empty space is there? These are all things that are being worked in more detail. But just from that, seeing those first Draco images, the same ones that we all saw together on that evening of the crash, where you just make out little individual rocks. This looks very characteristic of a rubble pile. Dimoprhos has been fascinating in itself as well, the larger asteroid. So maybe it didn't get as much attention and people weren't focusing in on it as much as we were zooming in on Dimorphos, but there's some great images that capture what Dimoprhos looks like in more detail than we've ever seen. And unlike Dimorphos, it looks like it has some patches that you can see in those images that are maybe not as rocky. And so people are really sort of questioning, what does this mean for how these objects formed? But there's still a lot more work to go. The fact that we're getting such an enhancement in the deflection of this 32-minute orbital period change is also a really good insight into how strong this object was or wasn't, and also is maybe indicative of it being more like a rubble pile, where you then were able to throw off more loose material more easily and enhance this deflection. But this is all getting borderline speculation now, so I should let the team come out with the real results sometime in there. But these are sorts of the initial things just from the data that we've been able to share so far.
Yeah, leave the speculation to us. We're the guessing professionals here.
That's right.
So looking ahead, this is a fairly small object. If you spot a larger object headed our way in the future, what are some of the other techniques you would consider for deflecting those?
You could still consider a kinetic impactor for a larger object. There is sort of an upper size limit there. A lot of these really just come down to not just the size, but the warning time. So warning time is really a key part of any discussion about what technique would you use. If you don't have very much warning time, you have very few options. And something like a kinetic impactor like DART is probably not one of those options then, if you don't have that warning time in order to do something. So it depends not just on the size, but on how much time you can identify it. And then that opens up this whole space of possibilities that I'm not sure which way I should go down first. But I'll also just say, though, something the size of Dimorphos is a priority object for planetary defense, because objects that are a kilometer or larger, over 95% of that population has been found, is being tracked, and none of them are a threat to the Earth for the foreseeable future. So it really is these few 100-meter sized objects that are sort of the ones that we have only found less than 50% of the population, about 40% of the population or so. And there's a lot more of those than the big ones. So just from a statistical perspective, we're much more likely to get hit by something that's a few hundreds of meters in size than the larger ones. And the ones that are a kilometer and larger, we found over 95% of that population, and they're not a threat to the Earth.
So
yeah, I think Rod also Bruce Willis is one of those options too, right? I mean, I'm surprised it's taken us this long to mention.
The option without very much warning time. Yeah, the Hollywood blockbuster options are not good. That's not the future you want to live in.
Well, actually,
it's very good for Hollywood, bad for reality. So yeah.
So that was going to be my follow-up question, because when you start talking about larger objects, of course, lots of people think about the movies they've seen. They think, oh, we'll blow it up. Well, it's hard to blow up a rock, and not always desirable. So when the idea of a nuclear intervention, a nuclear explosive intervention comes up, I guess one question is, would that achieve anything desirable, and what are the potential downsides?
Yeah, there's two parts there. So you could use potentially a nuclear explosion device in the same way as like a kinetic impactor to give something a small nudge. But the nudge would be slightly bigger. So maybe you had a slightly bigger object, So again, this is about deflection, not disruption. Those are kind of like the two.
So you're not trying to blow it up. You
wouldn't try to blow it up, but you would give it a bigger nudge by using a nuclear device in order to do that. So that's also one option for, more deflection, a more powerful deflection. You could scale your spacecraft. A lot of times people potentially consider multiple spacecraft, right? You don't just need one dart, you could have multiple darts, right? And they could hit in a series, in order to have nudge. But you always then want to be careful that you're not doing the disruption option if that's not what you're intending to do, because then you've gone from having one asteroid that is a problem to potentially having multiple asteroids that are a problem. And now you have many more problems than you did when you just had one problem potentially. So that's why that's really undesirable. There's just so many. What's nice about these deflection ones is that you're doing the minimal amount that you can do to just fix the problem that you have, right? There's not a lot of unknowns that you might create. Now, if you go to the destruction one, which if you don't have a lot of warning time, honestly, that still might be the situation that you would have to look at and you would have to weigh those. But this is a bad situation to be in and not the future that we're trying to create with planetary defense efforts.
Well, so I don't want to pull you too far into speculation land, but there was one technique discussed a few years back that I thought was really fun. Well, fun's a relative term here. You're talking about global destruction, but for objects of a certain class or size, essentially setting off a paint bomb on one side to paint it a lighter color so that the solar radiation is differentiated from the dark side and that actually pulls it off course. Is that something that's still being considered in the long term?
So we've been talking a lot about, these sort of instantaneous nudges for deflection. Another way that you can get deflection is more from these slow, continuous techniques, if you think about it, right? So this is still, again, very much on the deflection, not disruption side, and still something that you'd want to do many, many years in advance, right? Something that's a small little force that then adds up to a bigger change in its position with time. So, this like paint idea is one that's been published. Another one is this gravity tractor, where you go and you have a spacecraft that's close by and it just sort of tugs on it with this force of gravity. And it's a very, very small force, but if it acts continuously for many years and decades, then that can also shift the asteroid and just deflect it slightly so it wouldn't be on a course. Another one is the ion beam deflection, where you go and you sort of fire your little ion beam engine at it repeatedly. And again, this is not a very strong force at all, but if it acts over the course of, many years or decades, so this has its own challenge, because what you're essentially saying is that you want these spacecraft to go operate around these asteroids for many years or decades successfully in order to have this effective, like slow pull, or if you will, So, but these are both, these are other options. And I think it's exciting that like DART has taken this first step. It made sense to test the kinetic impactor first because it was the most mature of these technologies. It's a pretty straightforward sort of concept. But it's not the only tool that you want to have. I think everybody agrees that you want to sort of develop these other capabilities, and what that looks like is an exciting future that it'll be. I really hope that we continue to do more technology demonstration missions that advance other techniques as well as the kinetic impactor.
I guess to ask that, you mentioned, Nancy, that 95% of the really big ones, like the ones that are in the movies that are always endangering Earth. I'm sure that Earth gets tired of that after a while. That NASA's been tracking those, and I'm wondering what the risk was like must be or is. Like, are we overdue for some kind of substantial asteroid strike? I mean, I feel like we just had one in 2014 with the Chelyabinsk asteroid impact that got a lot of attention, and I know that there's asteroids that are passing by, just whizzing by every day, but they're fairly small. I mean, is it a serious risk, or just one that we should be doing missions like DART to be, so that we've got these measures ready? I mean, I feel like personally, I'm not really worried every single day about an asteroid hit, but what's your take on that?
I don't think people should be losing sleep over asteroid hazards, but it is something that we can take steps to do something about, and is something that has happened for billions of years in the past and will continue in the future. So I do think it's worth taking these steps to, build a better future where we can prevent this from happening. So Chelyabinsk is an interesting example because it's an object that was only about 20 meters in size. And something like this happens maybe every few decades or a century. So this is, a fairly common event even potentially, but something that's 20 meters, I mean, it's still caused a lot of damage to buildings, and it still injured over 1,000 people. And luckily it wasn't more than that. And luckily there was no fatalities. But you could see that something like that would be something you'd want to have warning time about. That said, 20 meters is still pretty small and not the size that most planetary defense is prioritizing right now. The size nominally is sort of this 140 meters and larger object. So very similar to Dimorphos size, these few hundreds of meters size objects. And the reason is because if something like that was to hit the Earth, that could cause regional devastation. And by regional devastation, I mean, damage going out for 10 to 100 miles, so that if over a heavily populated area, it could completely wipe out a city, a small state, a small country, that kind of thing. And so very rare. These are rare events for sure, but the devastation would be so dramatic and so regionally devastating that it makes sense to take these steps to do something about it. And that size population, much bigger than Chelyabinsk, is the size that we still have found less than 50% of that population. Mm-hmm. So finding things that size, these sort of city killer size, if you will, and then being able to also potentially prevent those if we needed to at the same time is really the focus and the priority for planetary defense.
Great. Well, I guess, I had one last question just to follow up, because it sounds like DART was fairly near, the results of it, fairly near to your heart. When Hera gets there, is there a chance that you could see, the remains of DART in the crater or around there and have like a moment of silence for its sacrifice for the greater good?
We've modeled that and asked our questions themselves. So people on the team have looked at this. So this is not a new thing. And most people think that it's going to be pretty smashed into pretty small pieces, but potentially some people think maybe, pieces of the solar arrays that stuck out but didn't have very much mass in them. Maybe some of those would not be completely smashed and might be resolvable by Hera. We will definitely look. And I think it's a lot of people ask us too if we're sad about DART, or your moment of silence kind of alluded to, whether we should. And a lot instead, I think people are really proud of DART, right? Like this is what DART was designed to do. This is what DART was built to do. And it's, it performed amazing. This was its moment. The world was watching, and DART just exceeded expectations and was a bullseye, like you said. And so everybody's just very proud of this. I think there's just celebration, not moments of silence.
So just for my last question, and you've kind of touched on this, but I wonder if you could expand, what are the next steps in planetary defense, especially with regard to proof of concept missions like DART?
I mean, planetary defense is an international effort, which is very exciting. So everybody sort of has their next steps. Hera going and along with DART, and Hera team members are on the DART team, and DART team members are on the Hera team. We have a very international team, along with the telescopes all around the world that have been helping with DART. And so it's really exciting that even after DART, there's the Hera mission, where we're going to continue to learn from this first test and continue to understand more about applying this kinetic impactor technique going forward. But again, these mitigation options just need to go hand in hand with this larger planetary defense strategy. The larger strategy of identifying the asteroids, characterizing them, finding out where they are, and working internationally and assessing the situation. And so, NASA's next priority for planetary defense is the Surveyor mission, like we've been talking about, and that makes total sense. It might not be as smashing as DART, but it's the foundation of everything else that comes forward.
All right. Well, we'll make sure everybody sends in those cards and letters supporting Surveyor. Nancy, thanks so much for making time for us today, and thanks to our listeners for welcoming you to the show. And where can we best keep track of the DART mission and your other activities moving ahead?
Well, the website's always a great place to see this. So www.nasa.gov/DART mission. There's also hashtag DART mission all over social media, so you can follow along there, and stay tuned, because it's only been slightly over 2 weeks, and we've got a lot more to learn and a lot more data still to come, and we're looking forward to sharing that as the team continues to work.
That's great. Thank you. Tariq, where can we keep track of you?
Well, as always, I'm at space.com, dear listeners, and you can find me at Tariq J. Malik on the Twitters as well. Looking up, we're at the mid-month, so Halloween is coming this weekend you'll find me in the yard putting up all my decorations. So.
Well, now there's major news. And as if people don't know it by now, you can track me at pylebooks.com or on @astromagazine.com. Also on Facebook, Twitter, and occasionally Instagram when I think of it. Please don't forget to drop us a line at twis@twit.tv. That's twis@twit.tv. We welcome your comments, suggestions, and ideas, mostly. And thanks for joining us for this discussion with Nancy Chabot. It's been great. And we look forward to talking to you again. Don't forget, new episodes of this podcast publish every Friday on your favorite podcatcher. So make sure to subscribe, tell your friends, and give us reviews, because we live and die by reviews. 5 stars or a thumbs up will do nicely. And you can also head to our website at twit.tv/TWIS. That's twit.tv/TWIS. And you can follow the Twit Tech Podcast Network at Twit on Twitter and on Facebook, and twit.tv on Instagram. Do it all. Thank you, and we'll see you next week.
Listeners of this program get an ad-free version if they're members of Club Twit. $7 a month gives you ad-free versions of all of our shows, plus membership in the Club Twit Discord, a great clubhouse for Twit listeners. And finally, the Twit Plus feed, with shows like Stacy's Book Club, The Untitled Linux Show, The Giz Fizz, and more. Go to twit.tv/clubtwit. And thanks for your support.